morning to everybody. Welcome to this third seminar of the DUS Colloquia. Today we have the pleasure to host as presenter Professor Romain Postoyan. He received the engineer degree in electrical and control engineering from ENSET in France in 2005. Then his master's degree from the Coventry University, United Kingdom in 2006. PhD from Université Paris Sud in 2009, and actually since 2010 is research assistant at the in 2010 he was a research assistant at the University of Melbourne, Australia, and since 2011 is researcher at the Centre de Research and Automatique de Nancy, France. Please, Romain.
Thank you for the introduction and for the opportunity that you're giving me to give this talk. Yeah, it's a pleasure. So in this work, we're going to talk about a dynamical system evolving in discrete time, which are controlled by one of the most important algorithms of dynamic programming, which is called value iteration. And we're going to focus in particular on questions concerning stability, near-optimality, and when to stop this iterative algorithm. This work is essentially the PhD work of Mathieu Granzotto, which we supervised with Jamal Dafouz at CRAN in Nancy. And this work was done in collaboration with two other people, Lucian Bezoniu from TU Cluj in Romania and Dragan Nezic from the University of Melbourne. So at a high level, first of all, so we're going to talk about dynamic programming, which is really important in various fields, obviously in optimal control, but also in operational research and reinforcement learning. And it's a well-established field, I would say, which has been laid down starting from the 50s, 60s of the last century. But still, there are numerous open questions in our opinion. And as control engineer, we are particularly interested in the question of the stability of the closed-loop system. So what do I mean by that? We have a dynamical system. We will generate its input using an algorithm from dynamic programming. And the question we would like to ask is whether the closed-loop system exhibits some stability properties and whether the stability properties are robust in a sense that I will specify later. And so in this talk, we're going to consider on one algorithm coming from dynamic programming, which is called value iteration. And I use the acronym VI. I will use as less acronym as possible, but this acronym as possible, but this one would be important. VI. And again, our main scope would be to ensure stability property for the closed loop system. So let's be a bit more specific. So as I said, we consider discrete time system. Okay, so K is the time. It evolves in the set of positive integers. And deterministic systems, so no stochastic things here. So X is the state of the system, and at each time step, it takes values in Rn, n is any strictly positive integers. And it evolves according to these nonlinear dynamics. So F is the vector fields, and U is the control input. We can consider the case where the control input is constrained, so it only evolves in some certain set calligraphic U, which does not depend on X. And it's a calligraphic U of X is just a non-empty set of admissible inputs. The possible inputs we can pick given an X. Okay. So sometimes it can be everything, sometimes it can be a compact set, or it can be something more general. So in general, we look at that sort of models. And what we would like to do is we would like to minimize, to have inputs here which minimize a certain cost, which is given by this form. So the cost has an infinite horizon. It goes from K equals 0 to infinity. And it depends on the general stage cost here, L, which may depend on the state at time K and the input at time K. We only require at this stage that L takes non-negative value. Okay? At this stage, it doesn't have to exhibit positive definiteness properties and things like that. And what is very important, because it's essential in many dynamic programming analysis, is that this cost is discounted in the sense that this term here is weighted by gamma to the power k, where gamma is the so-called discount factor, so constant between 0 and 1. But actually, our result allows to consider the case where gamma is also equal to 1. Okay? In this case, it's not a discount factor. We're going to still consider this general case. And again, what we would like to do is to generate inputs which minimize this cost. And the optimal value function, assuming it exists, and I'll be more specific on that later, is given by this. So we call it V gamma star, which is the best cost we could get given an initial state X. And what I call, I've forgotten to mention that U bold is just a set of inputs in the set each time U and of admissible ones. So of course, something I didn't mention, if you have any question, feel free to interrupt me. I'm happy to clarify something. So at the moment, we have, again, nonlinear discrete time system, a general cost function which this is counted, and we look for a sequence of input which minimize. And how do we do that? How do we do that? So we recall that the optimal value function, so the best cost, is given by this expression. And what is fundamental is that this cost satisfies the so-called Bellman equation, which is this one, which is at the heart of dynamic programming. And V gamma star of x is equal to satisfy this equation. Okay? And so given this equation, the input we should apply at given x is given by this. Is one of the minimizer here of this equation. So here it's u, not a bold u, just a scalar, just a vector. And so to compute the given x, the optimal input we should apply, we have to solve, I mean, to select u0 star of x within the argmin, which may be non-unique, so within this set. So to compute the optimal input, we need to know V gamma star. But to compute V gamma star, we need to solve this equation. And this is really hard. Why? Because essentially we have V gamma star on both sides. So except in some special cases, like when the dynamics are linear and the cost is quadratic, we can do that. But otherwise, it's really hard, if not impossible, to do so. Okay? So we cannot directly apply this in general. And what dynamic programming does is to provide iterative algorithms to approximate this value, this function, based on this equation. And let's present briefly value iteration, how it proceeds. So I just recall here Bellman equation that we've seen on the previous slide. And value iteration works as follows. We initialize the algorithm with some function. We call it V gamma because it may depend on gamma 0 because that's the initial step. Okay, it will take typically non-negative value. And what we do, we iteratively apply this equation. So at step I, we're going to, given a cost V gamma I, we're going to compute the cost at the next iteration by solving this equation. And we can see the strong link between this and the original Bellman equation. In Bellman, we have the same optimal value function on both sides, while here we have the value function at the previous step and the value function at the next step. Okay, and this is fine because while here we have the same function to guess, this is given at step I, and then we can compute Vi plus 1 based on this equation. Still, it's not trivial to solve this, but it's much easier than that. And I'll go back on how to compute this later in this. And then it can be shown that if we keep doing so, under some mild condition, let's say we can prove that the sequence of optimal of value function, not optimal, that we get at any step, will converge to the optimal one as I goes to infinity. So it's really a way to generate near-optimal inputs. Then the more we iterate, the closer we will be to the optimal value function. Okay. And the question we would like to ask and to answer in this talk is to say, okay, now I've got my prompt. I use VI to generate my input. What can I say about the stability properties of the closed loop system? And once we answer this, we would like to make sure that this stability property is robust in the so-called nominal sense, in the sense that we would like to make sure that the vanishing perturbation, which may be arbitrarily small outside the attractor, does not destroy stability. So typically with continuous time system, in general cases, once you get stability, if we perturb a bit the system with a vanishing perturbation, stability will be preserved, let's say. But for discrete time system, in particular discontinuous one, this may not be true. We may very have stability, but then an arbitrarily small perturbation may destroy it completely. And we would like to make sure that this does not happen. Okay? So once this is established, that's what we would call robust stability. What is really interesting, what was not our primary purpose, but we realized that along the way, is that once we can prove some stability property for the closed loop system, we can really improve a lot the analysis of the near-optimality of the algorithm. What do I mean by that? Is how far is this guy at an iteration I to the optimal one? This is a central question in dynamic programming. We know that V gamma I will converge to this value, but when we stop it, how far we are? How far are we from the true one? And we will see that we can provide new bound based on stability. The last point we will see together this morning is we will discuss the implementation of VI, because the equation I've shown before is an ideal one. In practice, we never solve it exactly, and it's important to have results which also work when we do not implement VI exactly, like stability and so on. Okay. So there are already works in the literature on this problem. They all consider, as far as we know, undiscounted costs. So the novelty in this work is that we can consider discounted costs. We also work with more general assumptions on the plant and the cost function. We can investigate set stability and not only the stability of a point, which is typically the case in the literature. We also make sure that stability is robust, as I mentioned before. And also we have noticed this near-optimality analysis, where the idea is again to exploit stability to improve the mismatch between the value function we obtain and the optimal one. So the talk is organized as follows. So I'm done with the introduction. The main part will be to talk about these robust stability guarantees. This is the most technical part of the presentation. The more we go, the less technical I will be, because in the next section, I will just concentrate on the main ideas and the main messages. So we will see robust stability guarantees, near optimality, provide an example. And then in section 5 and 6, we will essentially talk about how to implement value iteration in practice. And finally, I will give some conclusions. So let's move to robust stability. The first observation, which is essentially in our work, and it's not due to us, some other people have noticed this before, is that essentially there is a very strong relationship between the value iteration and model predictive control. Why? So let's suppose that we initialize VI with the zero function, which we are allowed to. Okay? And that's what we will do in the rest of this presentation. So we initialize our algorithm with the zero function, and then we apply it. So at step 1, V gamma 1 of x is given by this equation, while here we have V gamma of 0. This is just an application of the equation we have seen on the previous slide. Okay. But this guy is equal to 0. Okay, so V gamma 1 of x is nothing but the minimizer of LXU for given x. So now if we move to step 2, V gamma 2 of x is equal to this, satisfy this equation by definition, while here it's V gamma 1. Okay, we use the value we have obtained before. But this guy is given by this expression, so we can replace it. I just use u prime because it's not the same u here. Okay, this is just the application of this formula. Since LXU is independent of u prime, we can move this minimum over here. And at the end, what we obtain is the minimum over u prime of this expression. But this we can write it equivalently, it's equivalent of this minimum of u over the u0, u1 of this cost. And what it is a finite horizon cost, which is discounted. And if we keep doing so, what we obtain is this. At iteration I equal d, V gamma d of x is nothing but the minimizer of this finite horizon discounted cost. And this is a tip. So, and then what we do essentially by solving VI, we solve a finite horizon discounted cost. That's where the link with model predictive control is done, because in model predictive control, typically we solve finite horizon costs. There may be a terminal cost here, which will appear if this guy is different from 0, but often there is no discounting. But once we do this observation, we say, oh, maybe there are results in the literature to address this with this angle view, this viewpoint. So, oh, I remove one slide. That's interesting. Ah, no. Okay. So just before I explain that, so at the end of the day, what we've seen, we have this model of the plant. And at iteration d, we minimize this cost function, V gamma of d, where d is the horizon, is this. Okay. So the horizon of the cost is equivalent to the number of iterations of value iteration. And the closed-loop system is described by that. X of k plus 1 belongs to, I will explain why there is a belong, f of xk, and uk, what it is, it's the first element of the sequence which minimizes this cost. That's what is written here. We take the first element about the sequence of input which minimizes, just like in MPC, and we obtain this closed-loop system. I've put a belong here because the set of minimizer may be non-unique. So that we have a difference inclusion at this stage, something which may be discontinuous. Okay, and we call it f of gamma because this depends on gamma, and d, it depends on the horizon, equivalently on the number of iterations. So there are results in the literature, to assess the stability of such system with the minimizing this discounted finite horizon cost. The answer, to the best of our knowledge, is no. So when there is no discount, then there are many results which we can find in the model predictive control literature. I just cite one here because we were strongly inspired by this work by Andy Thiel and his cohort. But okay, so now when there is a discount, the only results we are aware of is when the horizon is infinity. And this is something we solved before in the previous work with essentially the same co-author. Mathieu wasn't with us, but this is the same. So what we are doing here, what we need is essentially to combine these two sets of results. Those which allow for finite horizon costs and those which allow for discounted costs. At high level, it's kind of easy. The assumptions are very similar in the two papers that I refer here, but technically it's really hard because of the interplay between gamma and the horizon D. And so how do we do that? So we make a set of assumptions, obviously. The first one is that we assume that at any iteration D, the minimizer is well defined. We can define V gamma of D. That's what is written here. So for any state X, any discount factor gamma, which may be equal to 1, any horizon, which may be equal to infinity, we can find a sequence of length D of input, which minimizes the cost. That's what is written here. So this U gamma D star is an optimal sequence of input, which minimizes this cost. So this is a minimum, and we can define V gamma D as we've seen. How do we ensure this condition? Well, for instance, when F and L are continuous, when the set of admissible input is compact, we can prove that this condition holds. We need maybe an extra one, but it's okay. But in general, sufficient condition to ensure this can be found in this paper. So this is essentially what we're saying here is that VI is well posed. At any iteration, there exists a minimizer. That's all we need. So now that the algorithm is somehow well posed, we need to make some assumption to be able to talk about stability, stability properties for the closed system. And just before stating this assumption, I would like to point out one thing is that, as I mentioned, we would like to talk about stability, not only of a point necessarily, but of a set. So what we do for this, we introduce some function sigma, which takes X as an input, as an argument, so stuff which are in Rn, and returns a non-negative number. We need sigma also to be continuous. So for instance, if we want to study the stability of the origin, we can take sigma of X to be equal to the norm of X, or to the norm of X squared, or maybe to some quadratic form, positive definite of X. But we can also define sigma to be the distance to a certain set A, or there is a typo here, which I need to modify. I will send you an updated version. Okay, so this is just a convenient way to define stability in such a way. We will use sigma to define stability so that we can cope with set stability as a particular case. Okay. And if you're familiar with that, it's really related, but a bit different to what we call two-measure stability, investigated by people like Laurent. So sigma is not really a measure. Sigma is really a way to know how far is the state X to the attractor that we consider. Okay. So, and what we make as an assumption, given this sigma, we make first a stabilizability assumption, in the sense that there exists alpha bar V, a k-infinity function. So what is a k-infinity function? It's a function from R plus to R plus, continuous, positive definite, strictly increasing and unbounded. So if you're not familiar with this, we can just replace it. You can just replace it in your head with a strictly positive constant times its argument. It would be like alpha bar V times sigma of X when this guy is strictly positive. This will still convey the main message of the slide. So there exists such a function so that for any discount factor, any horizon, and any state X, we can upper bound the optimal value function by this term. And I recall that this is the optimal value function, which is actually a minimum in view of the previous assumption. Why do I say that this is related to the stabilizability of the system? Because there is this result adapted from the work by Jim Grimm and co-author, which says that if L, the stage cost, is globally exponentially stabilizable, as I will show here, then this assumption is verified. What do we mean by that? It means that there exists some strictly positive constant, such that for any state X, there will exist a sequence of admissible input which will drive this term to 0 exponentially fast. Okay, this is essentially what is written here. And once this assumption is verified, we can prove this, and the proof is sketched here. So V gamma of D of X is the optimal value, the optimal value function for the finite horizon cost. So this is less than what we obtain when we consider this sequence of input, because this is the optimal one. And this sequence of input, we can write this term like this by definition. And we know that L of xk uk is upper bounded by this term, by assumption. This is a geometric series with the exponential minus lambda k, so we can compute it. And we can then, there is a mistake here, it should be less than or equal. Sorry for that. I will update the version on this. So we can upper bound this term by this, and this defines a k-infinity function of sigma of x. So it's a strictly positive constant of sigma. So again, the idea here is to say that if for any x, we know a sequence of input which drives L of xu exponentially fast to 0, we can prove this condition. But it's just a sufficient condition. That's why the assumption, this property is really related to the stabilizability of the system. The third assumption we make, and that will be the last one, is a detectability assumption. Why? Because what we do when we optimize this cost, we essentially put L to 0, roughly speaking. And by bringing L to 0, we would like to make sure that the state will follow and converge to the attractor. That's what this assumption is saying for the Lyapunov base arguments. So to be a bit clearer, we suppose that there exists a continuous function W, which may be equal to 0, some k infinity function, alpha W, k W, chi W, and some function here which is just continuous and 0 at 0, such that this property holds. Okay. And maybe the best way to see it is to look through a common example in control. So suppose that the stage cost is quadratic. So L of xu is x transpose qx, but u transpose ru, with q and r positive, q positive definite and r just positive semi-definite. And in this case, this assumption holds because let's see that. So we can take w, which is equal to 0, okay? So that this obviously holds, we can take any function alpha bounded. But we also observe that by definition of the stage cost, Lxu is greater than x transpose qx, because r is a positive semi-definite. And since q is positive definite, it's greater than the minimum eigenvalue of q times the norm of x squared. And this guy is strictly positive. And so what we see is that so we have already seen that this assumption, this condition holds. So for this one, what do we have in this case? We have 0 minus 0, because w is equal to 0. And we can prove then, if we can take chi w to be just the identity. So this is just L of xu. And indeed, this term is greater than this term that we would put here. So by doing so, what we see is that when we take a quadratic stage cost with q positive definite and r positive semi-definite, we do satisfy this condition with sigma of x equal norm of x squared, w equals 0. Any function here, we can actually take 0, chi equal identity, and this function alpha w of s, which is equal to lambda min of q s squared. Or there should be a square. No, there is no. Oh, maybe a square. No, it's okay. It's an s. Okay. So what's the idea here is that this is just an example to show how this is related to detectability. So at a high level, what we have made as assumption so far is first that the VI is well posed. There exists a minimizer. Second, the system satisfies some stabilizability property and some detectability property. And this is really consistent with what we do for linear quadratic optimal control. If we want stability, we need these two properties as well. So what we've seen is just like a nonlinear Lyapunov-based version of the condition we typically use for LQ. This is just to say that these assumptions are natural in our opinion because of that. So now the next two slides are the most technical one of this presentation. I would just like to give a flavor of the analysis, the Lyapunov analysis, which allows us to prove stability. So what we start with is this value function that we obtain at step T. It's given by this. And by stabilizability assumption, we know that this guy is upper bounded by this guy. Okay, this is just something we assume. Now let's try to lower bound this thing. So V gamma of D by definition is this, where U star of X is just some sequence of optimal input. And if we decompose this term by term, we obtain L, what happens at K equals 0, K equal 1, and K equal D minus 1 or D whatever. Maybe there is D minus 1 here. See, not so important. But this is a sum of non-negative terms. So this is greater than the first term, L of X, U star 0, because all these guys are non-negative. So now suppose the detectability condition we've seen before holds with W equals 0 and chi W are less than identity, just like in the quadratic case. Of course, our result applied to more generic one. This is just to convey the main idea. So by definition, W is equal to 0, and we have this inequality which holds. Okay? So this guy is greater than this guy. That's what is written here. But V gamma of D, there should be a D here, it's greater than L of X U star 0, so it's greater than this. And by doing so, we have actually proved that V gamma of D is positive definite and radially unbounded with respect to the set sigma of X equals 0. So we have the standard requirements, so to say, that V gamma D is positive definite and radially unbounded, which is the first requirement in the Lyapunov analysis. Now, the second thing we need to do is to look at how V gamma of D evolves along solution. And what I will do here, just to convey the main message, we will suppose that we have iterated VI infinitely many times, okay? And we will just concentrate on the effect of the discount factor, because that's easier to see. And then I will explain what happens when D is different from infinity. So in view of Bellman equation, we have this. So I put infinity here because we make the assumption that D equals infinity. So when we use Bellman equation, we have that V gamma infinity of x1 minus V gamma infinity of x0 is nothing that this term is the same, and we replace this guy by this guy, and that's what we obtain here. Okay, so this term comes here, and then we can put them together, V gamma infinity of x1, and they are multiplied by 1 minus gamma. Okay, so this is just the application of Bellman equation, and here we put together the term factor of V gamma infinity. And then we've seen by assumption that this guy is less than some alpha 0 sigma of x0. And this term is less than alpha bar v or sigma of x1. And after some manipulation, some computation, we can actually show that this is less, or maybe this is not the same function, but it's not important, of some function of x0, not of x1. And what we see is really clear. When gamma is equal to 1, the term in magenta disappears, and we have something which is strictly decreasing along the solution. But because of the discount factor, this may perturb stability, so to say. So we will need to ensure stability that gamma is sufficiently close to 1. And in general, this guy will not be able to beat this guy everywhere, even if gamma is sufficiently close to 1. Why? Because of what could happen around the origin and far at infinity. And because of that, we will typically have a semi-global practical result. In the sense that if we exclude any ball around the origin, if we exclude the infinity, so to say, we can find a suitable value of gamma such that we will have a suitable decrease on this conductor. And that's what is formalized in more general term in this theorem. We say that in general, if under more general condition than what we've seen on the previous slide, we can show that there exists a Lyapunov function V gamma infinity, which is positive definite, and satisfies the decreasing property here, where the perturbative term here, epsilon, can be made as small as possible by taking gamma close to 1. And this function, V gamma infinity, in the particular case we've seen before, it was V gamma infinity plus W because W was equal to 0. But in general, we have to do the so-called change of supply rates to make it work for the general case. But what's the idea here is that when we ignore the fact that the cost is a finite horizon, we suppose it's infinite horizon, this is a sort of Lyapunov analysis we can get. But now what we do VI with D strictly as an infinity, we have the similar result, except that the perturbative term here depends on gamma and D, and that to make it small, we need both gamma to be close to 1 and D to be close to infinity. It's just that it's more technical, but the idea is essentially the same. We can prove a nice decreasing property up to a perturbative term once again here that we can tune by tuning gamma and D. It's not enough to take gamma close to 1. It's not enough to take D close to infinity. Big. We need both of them to be big, essentially, with respect to their bound, 1 and infinity. And the shape of the Lyapunov function is exactly the same. In some cases, we can just take the sum of V gamma D plus W, the function we use to study detectability properties, or we have to scale them in a nonlinear way for this to work in general. Okay. And based on these Lyapunov properties, we can establish the next stability property, which is semi-global and practical, because once again, this term, in general, will not be able to compensate this everywhere. We need to exclude what happens around the origin and at infinity. And what we get is that for any delta, which is the size of the ball around the attractor, let's say, for any big delta, which is essentially the ball of initial conditions, there will exist a gamma star, a lower bound on the discount factor, a lower bound on the number of iterations, D star, such that if we take the discount factor bigger than gamma star, it could be equal to 1, by the way. If we take D bigger than D star, then for any initial condition in this set, this is some sort of ball, so to say, we will have this nice stability KL properties, which says that when k goes to infinity, this term goes to 0. And so sigma of xk would be less than delta. And again, delta we can tune. And this is a so-called semi-global because again, we have to set. It's interesting because we recover previous result of the literature when there is no discount or when the horizon is infinite. So it's just that our proof is a bit different, but you managed to do some nice changes. So the main message here is to say when we apply VI, we need to iterate it sufficiently many times and to have gamma sufficiently close to 1 to be able to get some stability properties. And that this stability property would be semi-global and practical in general. But under some stronger assumption on the k-infinity function that we have seen before, we can prove stronger stability properties, like semi-global asymptotic. In this case, we will converge asymptotically to the or global exponential. In this sense, the number of iteration and the discount factor can be the same everywhere in the state space, and it will work. It will last a bit. And so how should we tune gamma indeed? Because here I said there exists gamma star, there exists this star. The proof of this result gives some bounds, but they are conservative and not easy to compute. But we can get much easier compute bounds in these special cases. And what we noted, what Matthew have shown, is that in these special cases, we can even beat bounds in the literature, in the special cases when there is no discount or there is no finite horizon, the horizon is infinite. For instance, with the cubic integrator, Matthew have been able to improve by 63% the bound that we find in this work when there is no discount, and so on. So this is like an extra bonus, an extra result we didn't expect earlier. So now we have the stability property, and the system, the dynamical system we're looking at is this thing, a difference inclusion. And we know from this work by, it's not paper, but by the same group of authors, that we need to be careful. It's not because we have nice scale properties, stability properties for this system, that stability would be robust. They provide in this reference example of systems which do satisfy such property, but an arbitrarily small vanishing perturbation may completely destroy stability. So to avoid that, there are two sufficient conditions. Maybe I'm not sure they're necessary. One is that for any x, the set we obtain here is non-empty and compact. And that's the case that the assumptions we make. And the second one is that the Lyapunov function we use to establish stability is continuous. And if you recall, the Lyapunov function we use is this y of gamma d, which is some nonlinear function, continuous nonlinear function of v gamma d and nonlinear function of w. The rho are continuous. W is continuous by assumption. So to have continuity of y, we only need continuity of v. And we give condition in the work, mild condition, to make sure this is the case. So by doing so, we are sure that stability is robust. So-called rho perturbation will not destroy it. But I also think that continuity of v gamma d is interesting in its own right. Why? Because it's nice to know that if we start from closed initial condition, we have almost the same cost. That's what continuity is. It's essential for robustness, we saw it, but also important for learning. Yeah, question? No. It's important for learning because one way to add a learning, I would say, layer to that is to say, I don't know my system, I will learn my function on a compact, and then continuity of gamma d is really important. But here at least we have conditions for that. Okay, so now that we have this robust stability guarantees, we can talk about near-optimality. So recall that originally we wanted to solve this problem. But what we do with value iteration, at any step d, we solve this. These are not the same. And then the very important question in dynamic programming is how far are these two guys from each other? And what we can prove with our assumption is that the mismatch between these two guys can be upper bounded by this term here. So gamma power d, v, some function which depends on gamma d and sigma of x. And what is really important is that this term here goes to 0 when the discount factor is close to 1 and d goes, oh, I think it's only d goes to infinity. I'm sorry, I was confused. We only need d to infinity, and Mathieu can say when I'm wrong. We only need d to go to infinity to be correct. And also, this mismatch is small when sigma of x is small. So when we are close to the attractor, we have closed curves. Why is it interesting? Because when we look at the dynamic programming literature, the typical bonds we obtain are of this form. Gamma to the power d divided by 1 minus gamma. And what we have is that this bond blows up when gamma goes to 1. So when the discount is taken equal to 1, because they don't have stability guarantees in general, the near-optimality bound goes to infinity. And also this bound is constant. It's the same everywhere in the state space. While by exploiting stabilizability and detectability assumption, we can prove that bond here, our bond doesn't explode when gamma goes to 1. We can take gamma. And also the mismatch can be small, is small when we're close to the attractor. So the message here essentially is that classical control requirement, by classical control requirement, I mean detectability, stabilizability, do help for the near-optimality analysis. So now just an example. We consider like an inverted pendulum. We add more nonlinear, so just a sinus here, but we can consider other examples. And the cost we would like to minimize at iteration d is given by that. Okay, this is the stage cost. Here we put no discount. Okay, we could have put 1, but it's there is a discount. Sorry, for this typos. Because you will see in the following, I will remove the discount factor, so I was a bit confused. But here we should really add gamma to the power k. And then in this case, we can prove that our assumption hold with sigma of x given by this. And we can actually prove that we get some global exponential stability properties of the origin. So to implement VI, we have to do some approximation because the equation we've seen before are literally impossible to solve exactly. So what we did, we consider a compact set, we sample it, and we did some approximation of the number of the set of input as well to be able to implement VI. And by doing so, what we've done is the following. So we consider one initial condition, and we plotted the evolution of sigma along this solution. So the first plot to look at is when the red one, when gamma is equal to 0.85 and z equals 6. And then we see that we converge to 0. So to say stability holds. If we decrease a bit d, the horizon, to 5, it's still fine, but we see that it takes a bit longer, but still we can prove that we have stability. But now, if we keep the same discount factor and we decrease the horizon, so we take one iteration less, we take d equal 4, we have the black curve, and then stability no longer holds. We have lost it. Similarly, if we keep the same number of iterations, d equals 6, which was working here, but we decrease the discount factor, then we lose stability as well. So there is really the idea that if we don't want to get stability, gamma and d needs to be both sufficiently large. Not one of them is enough to be large enough. And we can prove essentially that that's what Mathieu generated. He considered different value of gamma and of d, and to get stability properties, we need both pairs to be stable, big enough, which is represented by this area on this plot. The blue points here are, let's say, values of gamma and d for which stability can be ensured, or is shown at least seen in simulation, and the red one is when we lose stability. So again, main message is to get stability, in this case for VI, we need stability property, detectability property, and gamma d sufficiently large. Okay, so now let's move. The remaining part of this presentation will be less technical, and we'll talk about the implementation of value. So we have seen that to get stability, we need a sufficiently big number of iterations, and we can provide bounds on this number of iterations. These bounds, in any case, they are often a bit conservative. And in the general case, when you get semi-global practical stability properties, these bounds are really hard to compute. Okay. So, but how do people do in the literature to implement VI? When do they stop it? Well, they do not count the number of iterations. The typical way to proceed is to say when V gamma d plus 1 minus V gamma of d is almost the same, is less than some constant epsilon in a given compact set, then we stop. So what's the idea here? If we see at some point that we do not improve much, at the next iteration, we stop the algorithm. That's just what they say. But then there are very natural questions which arise. What's the impact of epsilon on stability, on near-optimality, and how should we select carefully epsilon to get stability properties? So what we propose is, so this is just the equation we've seen on the previous slide. What we have proposed is to generalize this by considering a general function C stop, or stopping criterion, which depend on some epsilon, which may be a vector actually, doesn't have to be a scalar, and possibly of x. And what we consider in our work is that we can take x not only in the compact set as people would do, but everywhere in Rn. So example of C stop function can be epsilon, just as before, in which case epsilon is a strictly positive scalar variable. But it can be also epsilon and sigma of x. And again, sigma of x is how we measure the distance from the state to the attractor. Or we can do some sort of combination of the two, like some minimum of some epsilon 1 and epsilon 2 sigma of x. We can do many things. What we give in our work has some condition on C stop, and these are just 3 examples. Note that in this case, epsilon is really a vector. There is epsilon 1 and epsilon 2. And to make it short, long story short, under similar assumption as before, what I mean by that is stability, detectability, and well-posedness of VI, and some mild condition on C stop, which is our fine because we design C stop. We do what we want. We can first prove that with this condition, VI will stop. There will exist some iteration at which the condition is satisfied. And then we can prove stability. And in this case, we have semi-global practical result where the tunable parameter is epsilon. And something I've forgotten to mention is that in this work, we ignore sample. We ignore the discounter. We take gamma equal 1, but we could do the same when gamma is different from 1. Okay. And what is interesting to note, so we have a clear understanding of the impact of the stopping criterion on near-optimality, because we can prove that the mismatch between the cost we obtain at iteration d when we stop the algorithm and the optimal one is upper bounded by this some k-infinity function of c stop epsilon of x. So the smaller this guy, the closer both of them are. But often, the smaller this is, the more we need to compute. It has to be bigger. And the last point, to be technical, this cost is like an open loop cost. Say that is the cost we would obtain by applying the sequence of input to the given x. But in practice, what we do it in a receding horizon fashion. And the cost we will obtain along the solution is typically different at the end. Still, under some condition, we can prove it's a similar result for the so-called running cost. So we can relate the cost we obtain along the solution with the optimal one, and we can also show how its tuning epsilon can help to be as close as we want to the optimal. Just an example. So here we took a cubic integrator, so it's u power 3 here. We take this stage cost. In this case, the attractor is the origin, and sigma of x is defined like this. All the conditions that we needed before hold. And what Matthew did is he considered different stopping criteria. And I put them in blue here because with those in blue, we can ensure global exponential stability property. For the one in black, it's just a semi-global practical stability. And it's interesting to note that to get global exponential stability property, our previous result required 71 iterations. That was the bond we get from the result. By applying this stopping criterion, we see that we just need 3, 5, 6, 7, 8, I mean, much less iteration. And again, how the choice of epsilon would also impact the near-optimality property we get. Okay. I wanted to say something here, but I've forgotten. So yeah, something I wanted to mention is doing some sort of event-triggered way in this, because we really stop the VI according to the states somehow. But the drawback of this is we don't know in advance how many times we need to iterate. But on the other hand, it readapts to the problem, and we get a much smaller number of iterations needed to get stability. Okay, so the last part is about the implementation. I already say a few words about that. But so we call that VI is like this. We start from an initial value and then we iterate it in this way. Okay. And I say it's better than Bellman because Bellman had the optimal value function on both sides, while here this is none and then we have to compute. Still, this is really hard to compute in general. These are functions. There are infinitely many values to evaluate here. So what people typically do in the literature, they do not solve this. What they do this only in a compact set. And even though it's on a compact set, this is never done exactly, but with some errors. So it's also important to try to see how far the results we have presented so far can be adapted when we only work on a compact and with their errors. So first, we will concentrate on the effect of having this only on a compact set. And what we propose in a recent work is to do this for so-called homogeneous system. So I will not recall what the mathematical definition of homogeneous system. It's a bit involved, but I can already say that any polynomial system will satisfy this condition. So what's the idea? The idea when we have some homogeneity property of the system and the cost function is that we can just solve this equation only we are on a compact set, which is in blue here. So here I just consider a two-dimensional system to be able to depict it, but it's a good, I would say, case to understand what's going on. So suppose the system is of dimension 2. We only consider an ellipse. It could be a circle, but I would say any set which will circle like that the origin. By the way, it's a compact set of dimension -1, just 1 here, -1. And what's the idea? The idea is to solve our original problem just on this set. So take one point, solve essentially VI here, and then thanks to homogeneity, we can infer the optimal value function and the optimal sequence of input, at least that's a hope, everywhere on some so-called rays. And by doing so on any point, we can cover everything on the space. So let's say differently is that when the system satisfies homogeneity property, we have a rigorous way to define the compact set on which we need to solve this. Because by solving VI on this set only, we can infer properties everywhere. At least that was the original hope, and I will explain what's going on in general. Okay. So this idea is not new. People have done it in continuous time, but for discrete time system, there are much less results. We were only aware of two, essentially, these two references. And a restriction of this result is that they use a homogeneity notion, which comes from continuous time literature. And because of that, the result only apply to system of homogeneity degree 0, 1. So essentially linear system to make it a very strong assumption on the dynamics. What we've done in our recent work, we have exploited the new notion of homogeneity proposed in this work not in the context of optimal control, but for discrete time system, which is like a variation of the standard one, which is adapted to discrete time system in such a way that we can derive scaling properties of the solution. And this property also applies for any system which has nonlinearity given by polynomials, real U functions, and things like that in the plot and the cost. And by doing so, we can derive a new scaling property of gamma of d. So we know if we obtain v gamma of d at some x, how it will scale along a ray. Okay. And this scaling is essentially exact. We can exactly recover the optimal value function that we're looking at everywhere on the rays for some special cases, which include minimum time control and maximum ends of control. So minimum time control is I want to be as fast as possible in some set. Maximum ends of control is to say that I want to be infinite time in a set while using zero input as often as possible. But this is just from some special cases. In general, if we scale the value function along the ray, we will solve a different optimal control problem. The cost will be changed. But still, with this observation, what we propose is a new approximate value iteration algorithm, which gives guaranteed upper and lower bound on the true optimal value function we are looking at. And these bounds are worse and worse as we go to infinity, but when we walk close to the set that we're interested, they are down. And this is something we submitted to next CDC. So this was for the part on compact set. Now we also say that, yeah, but when we implement VI, there are also errors here. And we have proposed results, which I will go briefly on that, saying that suppose that instead of solving that exactly, we obtain an approximate version V hat, which is eta away from the true one, where eta is some function which depends on some parameters, epsilon, which are coming from the approximation scheme we will obtain from them. And to make long story short, we can prove that under this assumption that eta can be small when epsilon is small, we can prove a similar uniform semi-global practical stability. And we have pushed a bit further this result to only work on the compact and to consider errors in many places in a CDC paper, which presents this. All right, so I think I'm done with the main thing. So to conclude, this was just for we have seen stability guarantees for system controlled by VI, and I give the associated references. Recently, Matthew presented the work at L4DC on when to stop VI and the impact on stability and near-optimality. How homogeneity can be useful to compute, to implement VI with something with CDC, and first result, I would say, on approximate value iteration and the impact of this approximation on stability and optimality. And what we're doing now is to do the same thing for policy iteration. And so policy iteration, in few words, the idea is to start from a feedback law, to evaluate its cost, and to build up a new feedback law which has a lower cost, and to keep doing so iteratively. And there is a very famous result which says that if we start from a stabilizing policy, all the policy the feedback we will get at each iteration will also stabilize. It's true, but it appears that if we want to really rigorously analyze this, there are a lot of subtleties which arise, and this is something which we're understanding. We also started some work on stochastic system, and what we would like to do after is to also take into account learning on top of this. And I would like to conclude this presentation with this slide. So it's a bit catchy maybe by putting AI, but I'm convinced of this message, and I'll explain why. So dynamic programming, all these are essential in AI, and they are really powerful to provide near-optimal algorithms to compute near-optimal inputs. On the other hand, as control engineers, what we can bring is stability and robustness properties, but also improve near-optimality bound thanks to this stability and robustness. And under control-friendly assumption, stability, deterministic, which are very natural. But also, I'm convinced that we can also tailor the algorithm as they were originally formulated to suit our purpose. That's a bit what we did with the stopping criterion for VI, because the stopping criterion is part of the algorithm, and we've seen that we say that maybe the stopping criterion typically considered in the literature needs to be changed for doing what we want to do. For policy iteration, our current work also shows that we need to change a bit the algorithm. So the message again is, I'm convinced we should not take off the shelf this algorithm. We should understand why they work and adapt them for our purpose, so that they better work for our control application. And that's something which is even more obvious in a recent work we have done, where the problem is the same as before, except that the set of input U, so U takes values in a finite set. So in this way, we can represent this as some sort of switch system for which the switching signal is the control input. And to solve the same problem as before, so optimal control, near-optimal control of infinite horizon cost, discounted cost, we found an algorithm in the machine learning literature due to Romain, and very powerful for doing that. But it didn't suit our purpose. It wasn't for maximization and not minimization. And to go from one to the other was not easy. It has bounded costs in the sense that the stage cost had to take value in 0, 1, which is not natural for control engineers. We like, for instance, quadratic cost. So what we've done, we have changed the algorithm to apply for minimization and undiscounted cost as well, and unbounded cost. And then we can provide robust stability guarantees and exploit the fact that we know that the optimal solution exhibits stability properties to change the algorithm to improve its near-optimality bounds. And we also have decided to stop it by taking into account stability. We know essentially that the more we exploit, we implement, we compute, we let the algorithm do some computation, we know that we're close to the attractor, and then we can exploit this property to mitigate the computation costs associated. And this is something that is presented in this reference. Thank you for your attention. I'm done on my side. I'm happy to take questions now.
Thank you, Romain, for your very interesting presentation. Are there some questions or curiosities?
I have just a curiosity, Romain. It's a very interesting presentation, hard to follow when if you're not aware of the results already, but you explained the main ideas in a very clear way. So thank you very much. I was wondering, just a curiosity about detectability.
Mm-hmm.
I cannot see from the beginning how this comes into play. So
the analysis?
Yes. Why is this assumption useful? I mean,
here, for instance, because suppose, so let's forget gamma, okay? Suppose gamma is equal to 1.
Yes.
You see? So we get minus L of x0, u0. And essentially, I presented the things in a special setting, in strong condition. Essentially, what we need is that L is lower bounded by some function of sigma of x0. And this is related to detectability. Like when L is equal to 0, we are in the attractor. If we do not have a detectability, we will not be able to have a strict decrease here.
I see.
It's because it's detectable that we can upper bound this by this term. And this is done in this special case, when W equals 0 and we have this. So when L is lower bounded by this term, when this term moves here. In general, we need to add W to have this. But again, here, this is it. Without detectability, there is not this. And then without detectability, it would be hard to compute something based on. We have a negative term, but we don't know how negative it is in a way.
Thank you.
No, thank you for your question.
Some other questions?
Oh, yes, I have a question again on detectability, because in standard linear systems, detectability is the property of asymptotically, is the possibility of asymptotically reconstruction of the state from knowledge of the output and of the input of the system. But here, the meaning is quite different. Why this terminology is used?
Well, yes, but another way to see detectability is to say if some output is always equal to 0, then the state will converge to 0. Right? That's also another definition of detectability.
So I am not able to argue the last sentence. I am not.
Yeah, there are some audio problems.
Sorry. So what I want to say is that I agree, but another definition of detectability is that when the output is always equal to 0, the state will converge to 0.
Okay.
Right? And this is what we see here in a way. When L will be equal to 0 all the time,
okay,
then W will strictly decrease in a way.
Okay.
And it will
therefore the output L is a sort of output of the system.
Yes, it's a detectability with respect to L, because
with respect to L. Okay.
When we minimize this cost here, whatever, this thing, we bring L to 0, so to say. We push L to 0. We would like to make sure that by doing so, the state converges to the right.
Go to 0. Okay. And another question, is there some results with which address the case of state constraints?
So I guess state constraints may be included in the stage cost, right?
Where?
Here we could include state constraints inside. We could have a penalty which says that when we are in the state, it's 0, and when we are outside the state, it's infinity, for instance.
Okay.
I thought of it a bit. I would like to investigate this more, but the first answer would be this. But I would be interested. Another interesting question is, this is an obvious way to solve it, but whether we can say something about, because you're talking about safety in a way, to stay in some sense, whether we can infer this, what are the conditions on L so that this would work? And but it's a different question. And what I've said would just be a particular way to do so by hiding this. Because constraint on the input, we have it here. It's on the state here, I would add it here, would add a term. And this will be part of L. And then if the assumptions shown later work, then this will follow.
Okay, thank you very much.
Thank you for your question.
Along this line, Romain, looking at this equation, can you hear me?
Yeah.
What about to extend this equation to different inclusions? I'm just asking this strange question, let's say. I'm saying this because at some time you are working with maps, no? We are working with dynamics that are in the sense of different inclusions. And then I said, why not to start from the early beginning?
But yeah, then it's a min-max problem in a way, because we may have different solutions from one here. Because here there's a major difference. For one sequence of input, we only get one sequence of state.
I see.
Different inclusion, and then it's possible, but it becomes a min-max problem in a way.
Yeah,
but it's a really relevant question, and maybe that's what you had in mind, because when I was looking at this, I'm moving to another topic, and then you will see maybe why I'm saying that. I was thinking whether the tools used in symbolic control that you know very well, right? Which lead, because you have tools to get differential inclusion here, difference inclusion.
Yeah.
You have a rigorous way, let's put it this way, to get difference inclusion so that you work on a finite state. But then if you do that, again, the problem changes. It's a min-max thing. I haven't looked at that. There exists results in the literature, but we didn't look at that at the moment.
Okay. This is just
a relevant question. We thought of it, and we had the same observation, because when we saw a belong here, we said, why not to put a belong there? But again, it changes this.
I see. I mean,
because there are several costs. You have several costs essentially here. You want for any possible solution. So
I understand. Yeah. Thank you. Are there some other questions, curiosities? Yeah, Domenico, perhaps?
Yes, I have, but I am in a very unstable situation with the internet. So I hope to make my question. The question is, you need global exponential stabilizability of the system, right?
It's only a sufficient condition. It's a sufficient condition to prove the condition that what we need is this. What we need is this. But then what I'm saying is that exponential stability is a particular case, sufficient condition.
Exactly. Yes. And it is like a global exponential stabilizability property. My question is, can you weaken this assumption to just global asymptotic stabilizability?
No, we didn't look at that, but we could try to find cases. The big question is whether the series here we will obtain we will be able to upbound it by some function of sigma. But what we can do in general, so if we have just a function, we can change the state cost to get an exponential one. We will by some time. But if we have the L bond, we can exponential one. Do you hear me? Do you see what I mean?
Yeah, thank you. I'm sorry, but I didn't understand very well, but it's okay because I can hear very well. Thank you very much.
Sorry, maybe I can write an email if you want to, Johan.
Thank you. Thank you very much.
Let's see if there are some more questions. Well, it seems not. So I would like to thank very much Romain for this very interesting talk. And I see here also Marika. Thanks again, and goodbye then.
Thank you very much, Romain.
Thank you.
And have a nice 14 juillet. Have a nice 14 juillet celebration.
Thank you very much.
Thank you for giving the talk on a holiday.
Yeah, no, my pleasure. And John, I know I will send you an updated version of the slide this afternoon. We'll correct a few typos so that you.
Okay.
Thank you.
Goodbye.
Bye.
Bye to everybody.
Bye.
Bye-bye.
Bye-bye.
Ciao.